Welcome to Chapter 8, the last chapter in the course. We're going to start with 8.1, which is sequences and summation notation. We're going to talk in general about some of our notation and about sequences, and then of course summation notation. And then in 8.2 and 8.3, we are going to talk about specific kinds of sequences and so on. Okay? So first off, we need to know what a sequence is. We have a good gut understanding of what it is, but how is it defined in math? An infinite sequence, which is one that of course never ends, and it's written in braces, a sub n, okay? This is a function whose domain is the set of positive integers. So what this is saying is we're going to have a function, it's going to be written like this within, maybe in parentheses, like braces like this. And the only numbers we are allowed to plug in are 1, 2, 3, 4, 5, so on. We are not allowed to plug in negative numbers. We're not allowed to plug in 0. We are not allowed to plug in fractions. Okay? And because those are the numbers we get to plug in, 1, 2, 3, 4, it naturally orders the solutions. When you plug in 1, see right here, a sub n, if you're plugging in 1, you get a1. And we list it first. And then we plug in 2, and we get a2. Then we plug in 3, a3, a4, and so on. Now this is an infinite sequence written here, so we plug in 1, 2, 3, 4, and then however many we have to do to get to an, whatever an is, and then we keep going. Okay? Each of these is called a term. Okay? If you're asked to find a sub 4 of a sequence, then you're supposed to find the fourth term of the sequence. That sub number or variable tells you what number you're plugging in, or if you were to list them all, what would be in that position. Okay? Sequences whose domain consists only of the first n positive integers are called finite sequences. So it is possible that we have a sequence that only has 10 terms. And since it ends, it's going to be finite. So basically, what this is kind of saying is, here's our domain. And this is a sequence you'll recognize, and we're going to talk a little bit more about. If you plug in 1, you get 1. Plug in 2, you get 1. Plug in 3, you get 2. Plug in 4, you get 3, and so on. This sequence right here, we're going to be talking about more later. It is called the Fibonacci sequence. Okay, and it represents a whole lot of interesting things in math. But the way the sequence goes, the rule is you start off with 1 and 1. Those are basically given to you. You add these together, and that's your next number. Then you add 1 and 2 to get 3, 2 and 3 to get 5, 3 and 5 to get 8, and so on. So to find this number, you would add the two numbers before it. Okay? This one is defined recursively, which we will talk about in a second. Okay? Well, I didn't mean to mark that out. All right, we'll talk more about that later. Basically, that's the slightly more difficult kind of definition. All right, so let's just look at some of our easy problems. We want to write down the first 4 terms of the sequence defined by a sub n is 4n minus 1. Okay? So if I want to find a sub 1, then I plug in 1. So this is 4 times 1 minus 1, which would be 3. Now let's plug in a sub 2. We want to find a sub 2, which means we take a 2 and we plug it in right here. 4 times 2 minus 1. 8 minus 1 would be 7. And then a3, we plug in a 3. 4 times 3 minus 1. 12 minus 1 is 11. And then we have a sub 4. We were asked to find the first 4 terms, so this will be our last one. Plug in 4. 4 times 4 minus 1 is equal to 16 minus 1, so 15. Okay, So one thing I do want to point out is this is a specific type of sequence. This is the kind we're going to be talking about in 8.2. And notice to go from one to the other, we are adding 4 every time. So if you were to see this written out just as a list, your sequence would be 3, 7, 11, 15, and then you could keep going by adding 4 every time. That would be 19, 23, and so on. But we are only asked for our first 4. So let's look at this particular kind of sequence. Again, we're asked to find the first 4 terms. This right here, where you have -1 to a power, this takes care of alternating signs. And that's because, -1 is either going to be raised to an even exponent or an odd exponent, depending on what our end value is. If it's an even exponent, after we do the arithmetic, it's going to give me +1. And if it's an odd exponent, after we do the arithmetic, we're going to have a -1. So our signs are going to change back and forth. Okay? This is extremely common. So let's find a sub 1. So this will be, I'm going to write out everything here. -1 to the 1 plus 1 over 2 to the 1 plus 1. So this is -1 squared over 2 to the first power is 2 plus 1 is 3. So -1 squared is +1, so this answer is 1/3. That is our first number in this sequence. Let's find A2. This will be -1 raised to the 2 plus 1 over 2 squared plus 1. So this is -1 cubed over 4 plus 1. -1 cubed is going to be -1. 4 plus 1 is 5. Remember, with a fraction, your negative can be in the top, it can be in the bottom, or it can be off to the side. They're all the same values. Okay, let's do A3. -1 to the 3 plus 1 over 2 cubed plus 1. So this is -1 to the 4th power over 8 plus 1. So this is +1/9. And then one more, A4. This is -1 to the 4 plus 1 over 2 to the 4th plus 1. So this is -1 to the 5th power over 2 to the 4th is 16 plus 1. -1 to the 5th power is a -1. 16 plus 1 is 17. Okay, if you were to list all these, just list, if we were asked to list them, it would be 1/3, -1/5, 1/9, -1/17, and then it would continue. We started off with a positive, negative, positive, negative, and that's going to keep alternating as we plug in different numbers. Okay, now here we are again at the Fibonacci sequence. Okay, there are some interesting things that happen in here. First of all, you see this kind of, this sequence comes up a whole lot in nature. Okay, and there are other things about it. You may have heard of the golden rectangle in art. It is a rectangle that is supposed to be the most pleasing proportions. And for most of you, if I asked you to draw me a rectangle, you would come close to that. Okay, sorry. Now, another thing is, if you take any two of these that are side by side, you're going to get, and you do a division, you're going to get closer and closer to the number that defines the golden ratio. We're not going to go all the way into that. But again, this is supposed to be the most pleasing proportions. It is no accident that we tend to buy 3x5 index cards. 3x5. This is pretty much the golden rectangle. These are defined recursively, which is what I was talking about earlier. The way recursive formulas work is you will always be given at least one starting term. Okay? The Fibonacci sequence, you need 2 starting terms, but at least one. And then you're going to be given a rule to find the next one. So if I gave you 1 and 1, and then I told you that your rule is to add the two previous numbers together to get the new number, then you could do this. And I can keep generating this based on that rule. If I were given these starting points, I could do this over and over again, and I can keep going because I understand the rule. Now, it is harder if I just asked you to find the 1,000,000th term in the Fibonacci sequence. That's tricky, okay? But if you can set up a pattern and you know your starting point, it's not bad. Okay.